Hello, this is Dr. James Holt with the Engineering and Technology Management Program at Washington State University with another engineering management tidbit. This one I call the job shop game. It has to talking about choking and releasing the work to a system as a way to become predictable and fast. Just think about a job shop. Suppose you have a big shop with maybe 10, 20, 30 machines in there, 50 or 100, and you got 200 or 2,000 different things you make in there. Each part rotates through different machines at different times. Some of the parts get drilled first, some of them get folded, and some get trimmed, and some get cut. Some get taped and threaded, and some take longer, and some are short, and they flow through this job shop. It's a terrible scheduling nightmare. It's such a difficult problem that it's called NP complete, which means that we can't figure out how to optimize the system. And yes, we could calculate out the numbers, and we could also simulate it and try and figure out how to run it through. But what we find out is in order to find the optimal solution, it's faster to do the work than it is to calculate the optimal solution. This is a very difficult thing, but operations researchers love to talk about these NP-complete problems. I know I'm one, and I love to do that. The closest thing we have to solving the job shop game so far is the Little's Law, which says the amount of time it takes to get through there is proportional to how much dive you put in there. But still, we need to do a little bit better than that. So I invented the job shop game. Let's take a simple job shop. Here we have a simple one that we can probably grasp and put our hands around. It only has 4 operations, A, B, C, and D. Those are machines. And it only makes 4 products, product 1, product 2, product 3, and product 4. Each product flows through the job shop in a different way. The first one flows in through A to B to C to D, and then it comes out. The second one flows into B, and then to C, and then back to B, and then to D, and then out. The third one goes into A, and then to C, and then to D, and then to B, and then out. So each one, the fourth one goes to A to B, and then it comes back to B, and then C, and out. So each one takes 4 days to flow through 4 processes, and that's our simple job shop. Now, what we're going to do is we're going to play this job shop to build our intuition about how to handle such complex systems. The video for this that you're seeing now and the materials that you're going to see for the cards and so on are all located at this website, so you can go there and get those anytime. What we're going to do is we have cards. These cards are using for how to play the game. Each card is an order, and the elements on this card say at the top it tells you what product it is, and then it has a day that the work was released to the job shop floor, and then it has the space for each one of the job shop operators can write in their work. So in that box they write the work that they finished on that day. Each job shop guy can only write 1 card, 1 day, and in 1 box, and the cards have to flow in the sequence that they're scheduled to flow in this order. And the flow time, of course, is the last. At the bottom we can calculate from the time he finished his last operation, we subtract the day he came in, and that's the flow time to get through the system. There are 4 types of cards, 4 types of products, and when you print them out on the computer, they kind of print out like that, and there's marks there. You just cut them out, or you can make your own if you don't like that one. But you print out about 5 of these pages, or make 5 copies and cut them up so you have at least 20 cards in order to play the game. So we take our cards, and we're going to shuffle them up. So they're hard to shuffle, so you use the good old 2-year-old method of just shuffling the cards on the paper, because we shuffle them because, you know, when you're in a real world environment, you have no idea what job's going to come in on any particular day. Almost no job shop has control of what comes through their system, so let's be realistic and just shuffle them up and say they come in this random order, okay? So we've got those things shuffled up. Now, when we play, we're going to write on the card each time when somebody gets it. The person who starts the process writes in the top. That's the gatekeeper. And then he says, I'm finished. If you got work, work. And then at the end of the day, he says, okay, pass your card. So this one will be passed immediately to the A process. Boop. And that's how we do it. Let's see if I've got some animation here. in a minute. Each operator can only perform one operation per day, and they can write one number per day, and the operation is writing the number of the day in the box. And then the gatekeeper holds all these shuffle cards to make sure that he releases one every day to keep the job shop busy. So the job shop, the flow of the jobs look like that, and so they'll see in some of those jobs are not too busy. They need to follow the specified routing. You can't take a shortcut and move it to someplace else just because. You have to start at the top and work them in order. Sounds complicated, but it's really not once you see how it works. So the play is going to go like this. I have 4 cards here. Let's just assume that I'm starting. Okay, the first day is day 1. Let's assume that product 2 was day 1. We put a write a 1 in there. Day 1 is over. Nobody else has work, so we pass the card. Now it's day 2. The ordering person writes day 2 on card number 3, which happened to be the second one in line. And since process B has a job, he can write 2, still day 2 in his box. So that's how he does it. Now day 2 is order. We're going to move the cards to the next place. The day 3 is the gate operator is going to keep his. And then let's see, C has work, and A has work, so they can both report a 3. That's how that'll go. Now, when we see those things, we finish a card, we can see that we take the day that it was released and then the day that it finished on day 12, and so it took 8 days of flow in this case. And then we plot it on a grade sheet, which kind of looks like this, which tells us the history of how we're doing in our project. Since the order that we released on day 4 completed on day 12, so 12 minus 4 is 8 days. We put an X here at 8 days on the scatter plot. And then down below we put an X here on the histogram of 8 days. We'll probably have a lot more of 8 days. So we're going to keep a histogram of how many of them complete in how many days. And on the top we'll make a scatter plot that says how long does it take to get our tasks completed once we release them. Okay, so that's the way we're going to go. So let's try it. Okay, so here we have our job ship set up with our 4 machines, A, B, C, and D. They're the machine operators. I'm going to be the releaser, and I'm the only guy playing here, so I'll be not only releasing agent, but also be person A, person B, person C, and person D all at the same time, so it'll be a little confusing. It's better if you play with 5 people or so, but one person to do the cards, one person to do each job, and one person to keep track of the flow times. But we're not going to worry about that. We're just going to show you how it works here. And so here we have the first card. So I'm going to call out the day. It's day 1. If you have work, work. It's day 1, so I say I have work. I'll put it on and release it. Day 1 is over, so pass your card. Well, this job on day 1 goes to operator A, so I'm going to put it right there. Okay, day 1 is over. Pass the card. Now it's day 2. If you have work, work. So they're going to releasing agent says day 2. A has work, so he's going to write in here day 2. Nobody else has work yet. So day 2 is over. Pass your card. So this guy passes his card to C. This guy passes his card to B. Okay, day 2 is finished. Now it's day 3. So you write day 3 if you have work, work. So these guys have work. Good, doing great. Okay, day 3 is over. Pass your work. Well, this guy is passing to C, and this guy is passing to D, and this guy is passing to A. So that's how it works, just like that. So let's do a few days until we get to some histograms here to show how we record the values. Now it's day 4. So day 4, if you have work, work. So this guy has work, this guy has work, this guy has work. Almost finished here. Day 4 is over. Pass your card. So this guy passes his to B. That guy goes to B. Ooh, and this guy goes to B. And this guy goes to A. Okay, so now it's day 5. If you have work, work. So it's day 5. I have work here. I'm going to put 5. He has a day 5. Now, which one of these should I do? I can only do one. So let's see, this one came in last. I'd like to get something done, so we put it in here, day 5. Okay. Day 5 is over, pass. This guy is going to go to B. This guy is done, so he goes out. This guy comes into A. Now we finished one, so now we can record how it went. Let's see, it finished on day 5, started on day 1, so it only took 4 days. Very good. So we mark on our histogram for day 1, it finished at time 4. And this is our first product out. Excuse me, that's the scatter plot up here on the top. And then on the bottom we have a histogram say he finished at time 4. That's good. All right, let's play just a couple more days so we get the hang of it, see how this is going to look. So day 5 is over, we're ready for day 6. Day 6, if you have work. This guy works, this guy works, this guy works. Day 6 is over, so pass. This guy is going to go to B, this one's going to go to C, this one's going to go to A. Now it's day 7. If you have work. Day 7, day 7, day 7, day 7. And this one, 7's over, so move your cards. This one's going to D, this one's going to C, and this one's, oh, another B one. And this one's going to A. So we ought to play until we at least get one more out so we can know how the plot's going to look. Okay, day 8. Day 8, if you have work. So everybody's got work. That's good. We got efficient machines now. The day is over. Pass your cards. Aha, this one gets finished, so we'll put it up there. This one's, oh, he's got a B after, so he stays there. This one goes to C, and this one goes to D. Okay, so that one's going to come out pretty soon. Let's try this one out again. Because this one got released on day 4, and it came out on day 8, so it took 4 days. So it came in at day 4, finished out in 4 days, and we got another 4 days. So now we're going to see a plot of how things are going in our plant and a histogram of how things look. So that's how you play the job shop game. Okay, so that's the job shop game. You probably noticed that we had sort of a bottleneck over at the plant, the B machine, but hey, it was coming out. Well, because of that cumbersome nature of everything flowing around and getting stuck in piles up of stuff in different places, the traditional plot of how this thing works looks about like this. In the beginning, the scattergram looks kind of close to 4 or 5 days, and then it starts to get wild, and we see that some of the jobs get stuck in the system, and then it goes crazy on us, and it goes all over the place. And then since we stopped releasing cards after 20 days, we have 10 more days to get it out of there, and it finally gets emptied out. But the real question was, when do we expect a job, if we had continued releasing work every day until day 35, if we released a job on day 35, the 35th order, when would it come out? We can get sort of an idea if we just do a trend line upwards. And we see that, wow, if we had continued to day 35, it would have probably taken us like, 28 days to get it out. But it's 28 days plus or minus what? Well, we see, whoa, there's a lot of variability in here. It went from 5 days to 25 days on this particular example. So it's 28 days plus or minus 10, at least, maybe. That would be the best of the worlds. So it becomes very unpredictable. This is a real problem. We could probably need to figure out how to do this. If we play it again using the theory of constraints drum buffer rope approach, we can choke the release of jobs. The way we do that is we hold back the work. Instead of releasing a job every day, we look at our system and say we have a constraint. We're not going to put any more in that system than the constraint can handle. So just start by saying we're not going to release any more cards to the system if there's an empty B task in the system and the number of empty B tasks exceeds our buffer size. And the buffer size, if you don't know, start with like 5. So if there's 5 uncompleted B tasks in the system, don't release any more work because it's not going to be productive. It's going to drive you crazy. So we choke back the release. And then if B finishes some jobs and you get down to 4, you say, oh, we're below our buffer size. Then release a new job. If it happens to have 2 B operations on it, that's fine. Release it. And then wait until the buffer gets down below 5 again before you release another card. If you do this, choking and releasing, amazing things happen. What you find is the typical results then very similar to this program, meaning it's a very flat element. And as a result, the distribution about the flow becomes very tight. So you can be fast and very predictable. How long is it going to take to get your part out if you release it on day 35? Well, it's going to take about 8 days. So on day 43, that part will come out. Not 53 and not 63 maybe, definitely by day 43. Try it. You'll like it.